Thanks everyone for joining another Protocol Symposium. Today we have Hanzaleh. I've known Hanzaleh for a very long time, basically since I started working on blockchain stuff. Uh, he's a great researcher. Most of his work has been about coded computing, which is a field of study that focuses on this idea that we have, for instance, coding or things like erasure coding for storing the stuff. But if we have like faulty storage nodes, and there is a parallel in computing that like we have a distributed setting, we want to compute something in a distributed setting, and some of the nodes are faulty or malicious, can be used similar kind of ideas like we use in storage to add redundancy and like be able to retrieve the final result despite existence of like malicious or false. And I think this is the first work in that looks at like the problem of coded computing from the lens of game theory, in the sense that it considers incentives of players as well. It's a very interesting work that I've been meaning to like share and like learn more about. And I'm excited to have Hanzaleh here to tell us more about this. Thank you for accepting the invitation, Hanzaleh, and take it away.
Yeah, thank you. Hello, everybody. I'm very happy to be here. Thank you, Mo, for introduction. Yeah, all right. Okay, let me talk about game of coding. Okay, so first of all, this is a joint work with my supervisor, Mohammad Maddahali in University of Minnesota, and Vivek Kadambe from Georgia Tech Institute of Technology. Let me start. As Mo mentioned, the whole idea behind this work is to, try to analyze and evaluate coded computing through the lens of game theory. And the main motivation of this problem is decentralized learning. I'm going to skip the first slides. I'm pretty sure that everybody here agree with me that blockchain is good and we have lots of decentralized applications. So let me choose the starting point here. Okay. We have lots of decentralized applications, and most of them are very beneficial. We have Uniswap, Maker, Filecoin, and so on. And nowadays, specifically in the last years, people are talking about decentralized machine learning from different, directions and perspectives. So the main challenge to have a good decentralized machine learning based on blockchain is that we have a limited computation power. And what it means, miners in blockchain do everything, okay? They do consensus. They're participating in the consensus to maintain a consistent view among different nodes. They do settlement to verify everything. They provide data availability, something like the storage providing, and also they provide execution and computing, lots of algorithm. And in order to have a decentralized machine learning, one of the solution is to outsource the computation among different nodes. Okay, and the main way to do that is to utilize verifiable computing. Okay, I'm not going to talk about the details of different approaches for verifiable computing. Very briefly, in verifiable computing, we have some smart contract on Ethereum, which is a verifier, and the objective is to verify that the computation corresponding to calculating y equals to f of x has been done in a right way or not. Okay, so we have some external node that the computation is outsourced to that external node. And we have a verifier, as I've mentioned. The verifier is, can be literally a smart contract on the chain. And the external node, we are referring to that external node, external resource as the prover. And the verifier and the prover has access to some input x. It calculates y equal to f of x. And then through pi as the proof of the calculation. Okay, the verifier, based on receiving the result, which is y, and also the proof, try to verify all of this calculation, and whenever it accepts the calculation, the prover will receive probably something as a reward, and otherwise, if something is wrong, it rejects the computation. Okay, so this is a very briefly description of the verifiable computing. But if you want to use verifiable computing in decentralized machine learning, for example, we try to train the model or do any other heavy computation that is required in different layers of machine learning algorithms, the main challenge is that in order to generate the proof, and specifically for the case of machine learning applications, the proof generation process is very resource intensive. Okay, and in some cases, in order to generate the proof, you need to have access to a resource that is 40 times bigger than the computation itself. Okay, so it's very heavy. And because of this, we can't utilize these kind of approaches for the emerging use cases like LLM. Okay, and the other problem is that in most of these kind of verifiable computing scheme, we are limited to finite field operation and exact computation. Okay, all of the computation are within a finite field and everything in exact. So these algorithms don't support approximation computing. It's very hard. While in machine learning, the computation in lots of cases it's not exact. So and we have some kind of analog coding and approximate computing. Okay, so what is our solution? Instead of outsourcing the computation to a node that has access to a resource which is 40 times bigger than the computation itself, our proposed solution is to use coded redundant computing. So what does it mean? Okay, again, we have a data collector or verifier, which is a smart contract on the chain. And we have some, computing nodes. Let's assume that we have 4 nodes, okay? And the objective is to calculate f of x for some public function f. So the data collector announce or propagate or send this value of x to all of these computing nodes, and they independently calculate f of x. Okay, they don't provide any proof that claims that I've done everything in the right way. Just calculate the computation and send it back to the data collector. Also, in this model, we assume that the computation is not accurate, is not exact. So we have some accepted level of the noise. We can assume that we have an accepted level of the noise, which is plus minus delta. Okay, so the boundary of the noise is plus minus delta. This is the accuracy of the computation. Server 1 calculates y1, server 2 calculates y2, and server 4 calculates y4. All of them send these calculations, these values to the data collector, and based on the sent values, the data collector tries to estimate something and output something as y equals to f of x. Okay, and even for the case that, for example, one of the nodes, and in this example, server 1 or node 1 is adversary, using some schemes like median works very good. If you take the median, you can now easily prove that in this setting, which one of them are adversary and 3 of them are honest, the median of the y1 to y4 is in this accepted region. I mean, the computation accuracy is plus minus delta. Okay, it works. But for the case that we are not in the honest majority assumption, for example, between 4 nodes, we have 3 adversarial nodes, the median scheme doesn't work. Okay, and if adversary has access to more than the half of the nodes, I mean, we are not in the honest majority regime, the adversary can inject arbitrary error if the data collector is using median. Okay, so that's the case. And in fact, if we denote the number of honest nodes by h, the number of the adversarial nodes by t. For this scheme to work, I mean, using median and using repetition code, sending the same value of x to different nodes and try to take the median. In order to this scheme to work, we need that the number of the honest nodes should be bigger than the number of the adversarial nodes, okay? Which is a huge trust assumption, okay? So we need honest majority in this, mechanism. You may ask that, okay, this is a very simple coding scheme, and let's try something more advanced. For example, let's try to read Solomon code. Okay, if we try to use more advanced techniques like read Solomon code and, for example, log range coding, it's going to be worse. We need more honest nodes. Okay, so the main challenge is that if we want to use coded redundant coding, in these cases that we are not necessarily in the honest majority regime, we need a huge trust assumption. And the main challenge is that in the decentralized application, like decentralized machine learning, trust is a scarce resource. We can't guarantee at the application layer that at least half of the nodes are honest. Okay, so that's the main challenge. That's the main challenge of the classical coding if you want to use them for the case like decentralized machine learning. Okay, so we try to, here in this work, we try to introduce a new framework to resolve this problem and help coding theory to go beyond its fundamental limits, which is game of coding. So before going to the problem formulation for the general case, let's talk about the motivation, why we are going to define the problem in this way. Okay, if you remember, we have a data collector, we have some computing nodes. In this case, we have 4 nodes, and the computation accuracy was delta. It means that we have some level of noise that is accepted, and which is delta, okay? In this case, if the maximum of the y's and the difference between the maximum value and the minimum value that the data collector is receiving from the computing nodes is bounded by 2 delta, everything is okay. This is what we what is acceptable from the in the data collector side, because we have some noise that is okay. The computation accuracy is plus minus delta. So we may have some situation that in which the difference between the maximum and the minimum is 2 delta. Okay. So if this is the case, the data collector will accept the computation and estimate something as the output for y equals f of x. If it's not the case, the data collector rejects the computation. Okay. But the point here is that the data collector doesn't like rejection, because whenever the data collector rejects the outputs, we kill the system's liveness. And because the data collector like to keep the system live, so the data collector doesn't like rejection. Okay. On the other hand, the adversary also doesn't like rejection too. And this is for 2 reasons. First of all, in most of the decentralized applications, whenever the system is live, all of the participating nodes are receiving something as a reward, tokens, everything. Okay. So whenever the system is not live, it's been killed, the adversary will lose rewards. Okay. On the other hand, if the adversary wants to inject some error, if the system is dead, if the system is killed, there is no output. And once you don't have any output, you can't inject any error. Okay. Let's assume that all of this computation is related to, let's say, some financial application. And whenever the system is live, whenever the system is dead, it's not live, the system doesn't allow any transaction, any swap, anything, okay? But the adversary wants to inject some noise to utilize this opportunity in, let's say, arbitrage or whatever. And when the system is not live, the adversary can't utilize this opportunity. So the adversary wants to keep the system live for 2 reasons. First, receiving some kind of rewards, which is maybe token. And then if the adversary wants to inject some error, the adversary needs to keep the system live. So that's the case. It means that both the data collector and the adversary wants to increase the chance of the acceptance of the system or keeping the system live, while for the accuracy of the estimation or the computation, the data collector clearly wants to increase the accuracy of the estimation, while the adversary wants to decrease that. Okay, so we have two main parameters here: chance of the acceptance of the computation and the accuracy of the estimation. And for one of them, which is the chance of the acceptance, both of the player wants to increase that, while for the other one, which is the accuracy of the estimation, one of them wants to increase that, the other one wants to decrease that. So there's a tension here. As a consequence, the data collector may compromise accuracy for liveness, and the adversary acts rationally. Okay, so this observation motivates. It's good to have a game theoretic framework in which we have two players. Player one is the data collector and player two is the adversary, and try to analyze, evaluate, and do everything, process this kind of game. Is that clear? Do you have any questions? Or should I continue?
We don't have any questions in the chat, but I think it would be nice if you can give us a few examples that are closer to blockchain applications. So I think moving aside from I'm not sure if this applies or not, but I'm wondering, moving aside from the learning motivation, can we frame this problem as some sort of oracle
Yes, you can do the same.
problem?
Yes. For example, in the case of Oracle, we will see it more clear once I have defined the problem formulation. But even for the case of Oracle, let's assume that we have some nodes and they have access to a noisy version of some value, price, everything. Okay, for example, price of an asset which is not on-chain, and they have access to a noisy version of that. Okay, so the adversary wants to inject some noise, maybe to utilize some arbitrage opportunity or whatever. Okay, or maybe for some kind of DAO in order to deviate the DAO decision. For any reason, the adversary wants to inject the error. And also the data the honest nodes. So the level of the noise that the honest nodes are injecting and is accepted is, for example, plus minus delta. Okay, so the data collector doesn't have any idea for the case that the difference between the maximum amount and the minimum amount, once this difference is beyond 2 delta, in this case, the data collector doesn't have any idea which of these players are honest and which of them are adversary, because we are not in the honest majority regime. Okay, let's assume that you have two nodes. Okay, and one of them say something and the other one say another thing, and their difference is much. Okay, it's large. Okay, so you can't say which of them are the honest and which of them are adversary. All you can do in the classical coding, once you have this problem, you don't output anything. Okay, but we are trying to say something here, that if you analyze this problem from the lens of the game theory, we may have something which is useful, and we will see that we can keep the system live most of the times. And the reason behind that is that adversary acts rationally, and in order to act rationally, the adversary also have some motivation to keep the system live, and of course it has some motivation to inject some kind of error. Okay, and here the data collector can compromise accuracy for liveness. The data collector can say, okay, I'm not in the ideal case. I know that I'm not in the case that both of the nodes, in the case that we have just two nodes, both of them are honest. But you know what? Maybe I can compromise accuracy in the cases that the system is working and the level of the injected noise is in some accepted, boundary. So that's the motivation. That's the observation that, incentivized us to define this problem in a game theoretic setting. And you can observe this pattern both in Oracle and also decentralized machine learning, and anything that you have some computation outside the chain and you want to report something on the chain.
Can I ask a question?
Yep.
So is the assumption here that the hierarchy of preferences for the adversary are like, in the ideal case, it injects error and the output is live, and then the worst case is that nothing happens, or is the worst case that it like it's live and accurate? Which one of these is higher preference, I guess, for the adversary?
So okay. So both the adversary and the data collector, both of them has some utility function, and the adversary can have any utility function. Okay, maybe in some cases the utility function is just the probability of the liveness, and in some cases the level of the injected error, or in some cases it's some kind of any complex function of utility, liveness and the error. So that, and both of them has a utility function, and I don't care what is the utility function. So that's the problem formulation. Is that clear?
Yeah, I guess so. I guess my point is just like, if the hierarchy is such that if the utility function is such that the adversary would rather the whole system be down than an accurate result be published, then their incentives can be so misaligned that like the best thing for the adversary to do is just to always, make it make the thing go down.
Exactly. If this is the case, yes, that's true. If for any reason the best case for the adversary, once they have utility function, you can find the equilibrium of the game. Okay, maybe in some cases, I don't know, maybe the adversary, for some reason, for any reason, the equilibrium is that the system is always dead. Maybe that's the case. That's true. But what I'm trying to say is that maybe there are some situations that the equilibrium of the game, that I'm going to give some example. The equilibrium of the game is that, for example, 80% of the time the system is live, and 20% of the time the system is not working. Okay, so we always have safety, but for the liveness, we have 80% the system is live, and that's working. And for example, in the case of machine learning, it means that the convergence rate is 80% of the ideal convergence rate, that you have two honest nodes. Is that clear?
Yeah, makes sense.
Okay. Okay, let's talk about game of coding. Let's talk about the problem formulation. So here for this, talk, I'm keeping it very simple. So I will talk about a very special case that we have just two nodes, and one of them is honest and the other one is adversary. Once again, in the classical coding, once you have two nodes and one of them is honest and one of them is adversary, you can't output anything. The system is always killed. You can't output anything. Okay. Now let's assume that the objective is to the objective of the data collector is to have some estimation for u, which is the output of f of x. Okay. And u, we assume here that u has a uniform distribution from -m and m. So m is the range of the computation. Okay, the range of the computation could be from -m and m, and here for simplicity for this talk, we assume that u has uniform distribution. Okay, we have two nodes, one of them is honest and the other one is adversary, and we have a data collector. Each of these nodes has access to a noisy version of u in the case of Oracle, or the computation that they're supposed to do is not exact. And even for the case that both of them are honest, they will report something for u, which is a noisy version of u. Okay, so therefore y1, the output of the server 1 is u plus n1. And for the second server, we have y2 equals to u plus n2. And here, let's assume that The server 1 is honest, and the second server is adversary. Okay. For the case that we computate, for the case of the honest node, we assume that the noise distribution is symmetric and also it's bounded. Okay. Bounded between delta and minus delta and delta. So the range of the, and we assume that the range of the computation, which is M, is by far bigger than the range of the accepted noise by the honest node. So that's the assumption. But for the adversary, the noise distribution that adversary is utilizing can be anything. It can be, it's not necessarily symmetric, and it's not even bounded. Okay, it can be anything. Okay. So the data collector receives y1 and y2 in this simple example, and compare y1 and y2. If their difference is smaller or equal than some value of eta delta, if we remember in the last example, I mean, the first natural choice for eta is 2, because once both of them are honest, the difference is not exceeding 2 delta, okay? But if you remember, I've told you that the data collector is compromising accuracy for the sake of liveness. So it means that, okay, now I'm going to choose eta bigger than 2. Okay, we will talk about how to choose eta, but in the problem formulation, we assume that y1 minus y2, for some value of eta that we are going to choose, if it is smaller than their difference, y1 and y2 is smaller than eta delta, the adversary accepts the computation. And if it's not the case, so it rejects the inputs, it rejects y1 and y2, and there is no output. So the system is dead, it's killed. And once y1 and minus y1 and y2, their difference is smaller than eta delta, it will output something as the estimation. Okay? Using some estimation function denoted by EST. So we have some important parameters here. The first, let's define the acceptance event. And I think it's clear. The acceptance event means that this is the case that the difference between y1 and y2 is smaller than this threshold, which is eta delta. Okay? We have two main and important parameters here. The first parameter is the probability of the acceptance. Okay, the probability of the liveness. It's showing the liveness of the system, notion of the liveness. The second parameter, which is important, is the level of the noise that is injected by the adversary. And we define that as MMSE. So this is the MMSE, minimum mean square error, minimum mean square estimation function, which for each noise function the adversary is utilizing, the data collector will use the estimation function that, minimize the estimation error. Okay, and all of this is given the acceptance event. If you remember, whenever the we don't accept the inputs, there is no output. So there is no definition for the error once the system is dead. We don't have any output, plus we don't have any error. Okay. Once the system is live, given the acceptance, we will have some error, and the error is due to the estimation function that the data collector is utilizing. So we define the MMS in this way. Okay. And as you can see, this estimation function is dependent to the noise that the adversary is utilizing. And we will show this by EST star of eta, which is the parameter that the data collector is choosing, and G, which is the noise function that the adversary is utilizing. Okay. So each of these players, the data collector and the adversary, is utilizing, has some utility function. Okay. And both of these utility functions are dependent to the probability of the acceptance and the MMSE, the error. Okay. For the data collector, the utility function is a decreasing function with respect to the MMSE. Clearly, the data collector wants to decrease the level of the noise, and it is a decreasing function with respect to the probability of the acceptance or liveness. Okay. While for the adversary, the utility function is an increasing function with respect to MMSE, error, and also it is an increasing function with respect to the probability of acceptance. Let me give you an example. For example, here you can see for the data collector, it is an increasing function with respect to the probability of the acceptance, while it is a decreasing function with respect to the error. Also for the adversary, it is an increasing function with respect to both the probability of the acceptance and also the error. So this is just the only assumption that we are, using for the utility function. This is the only assumption. We are not talking about the convexity, concavity, and nothing else. Just there are some increasing or decreasing functions with respect to some variables. Okay, and in this game, the action set of the data collector is to choose eta, the threshold, to accept the computation. And the action set of the adversary is to choose the corresponding noise distribution. Okay, so this is the action sets of both of these players. I want to note here, if you want to define the equilibrium and try to analyze this game, the Nash game doesn't fit well. And the main reason is that here we have blockchain and a smart contract, and the data collector commits or submits its strategy, which is eta, in a chain. Okay, the data collector submits anything, commits, the rewards, policy, principles, and everything, the principles for the acceptance. It commits its strategy in the chain, and then the adversary chooses G, or the noise distribution, in response to the committed strategy by the data collector. So we have some ordering here. It seems that the data collector is the leader. It's committing something first, and then the adversary is doing something in response to the actions of the leader. So, and this scheme, leader-follower, is analyzed in some class of the games which are called Stackelberg. So here in this example, in this problem, we are utilizing Stackelberg games. And what I mean here is that, so the data collector commits to some value of eta, and then the adversary, in response to the committed value of eta, chooses a noise distribution that maximizes its utility with respect to eta, which I'm denoting by G star of eta. And the objective of the data collector is to choose some value of eta, which is denoted by eta star, the best threshold, in a way that it maximizes the utility of the data collector with respect to, by considering the response of the adversary to this value of eta. Okay, is that clear? I'm in a full screen mode, so I have no idea what's going on in the background.
I think it's a good place to pause and if there's any question. I think it's clear, like in the sense that it's clear for me why we are not in a scenario that both actors act at the same time, because we need data collector for the protocol to be well defined. We need data collector to commit first. Also
exactly.
So I might be biased because we have talked about this before, so I let others ask questions.
So hopefully everything is clear. Okay. As I've told you, so Nash game doesn't fit well here. We have a leader follower or Stackelberg game, and the data collector commit to some value of eta, and then in response to the committed value, the adversary chooses a noise, which is G star of eta. And the adversary, because the adversary is rational, the adversary chooses this noise distribution in a way that maximizes its utility function, okay? And the data collector knows this behavior, knows this response of the adversary, knows that the adversary is rational. And because of this, the data collector chooses the value of eta in a way that it maximizes its utility function given the response of the adversary, okay? And the objective is to characterize the equilibrium of the game, which is, the utility of the players by having eta star, which is the best value of committing for the data collector, and also G star, which is the noise distribution in response to choosing, eta star. Okay, so that's the objective of this problem. Okay. Now let's talk about the main results. Before going to the main results, let me convince you that it's a very complicated problem for two reasons. First of all, we have a very minimal and natural assumption on the utility functions. The only assumption here is that the utility function is a strictly increasing function for the adversary with respect to error and the probability of the acceptance. And for the data collector, it is an increasing function with respect to the probability of the acceptance, but it is a decreasing function with respect to the noise. Okay, that's the only assumption. We don't have any assumption about convexity, concavity, and because of this, we can't utilize a lot of well-established results about convex and concave problems. Okay, so that's the only assumption. The other problem is that one of the parameters here is the noise that the adversary is utilizing. And it's kind of infinite dimensional problem over all of the noise distribution that the adversary can utilize. Okay, so the adversary can choose any arbitrary noise, and we have different probability density functions, infinite dimensional probability density function, or PDFs, and that's going to make this problem also more complicated. Okay.
Can I ask a question?
Yep.
Sorry, can you go back a slide?
Back a slide, yes.
Yeah, I guess here you're saying that the assumptions on the utility functions are minimal, but just to confirm, you're saying that if you took the another way of saying the conditions on the relationship between the utility functions and those two variables is if you took the partial derivative of the adversaries, or sorry, if you took the partial of the what's DC again, the controller,
data collector.
Collector, yeah. If you took the partial of the collector's utility function with respect to probability of acceptance, it would be strictly positive. Is that right?
Yes.
So there is a complexity there where maybe the utility function is more complicated. It wants to maximize probability of acceptance, but there's some interaction between the terms that means that you can't the partial doesn't come out to be a constant. Does that make sense?
So the only assumption, it's a strictly increasing function. Okay, so that, there are a lot of cases that, clearly you can define some utility function that the utility function of the data collector or adversary is not, for example, for the data collector, it's not an increasing function with respect to the probability of acceptance. I accept that. But what I'm trying to say here is that the only assumption that I'm utilizing here in order to solve this problem is that for the data collector, it is a strictly increasing function with respect to the probability of the acceptance, and it is a strictly decreasing function with respect to the MMSE. Nothing else about the convexity, concavity, and nothing more.
Yeah, I got you. I guess I'm just saying I can imagine, and when I think of the first type of utility function that would make sense to me, for the data collector or the adversary, it often comes up that you would have some interaction between the terms. So you wouldn't even be able to make that assumption because maybe the data collector is okay with wants to increase probability of acceptance, but has a huge there's a huge utility penalty on any inaccuracy. So there's some interaction between MMSE and the probability of acceptance in that utility function.
Yes. That's a very good question. Practically, we may have a lot of utility functions that are not, considered in this problem formulation. That's right. Exactly. But here, as a first step, I try to evaluate this problem, and you're clearly right. I mean, in the next steps, I mean, that's one of the works that we have done in the last couple of months. The next step is to try to generalize this problem formulation and including these kind of utility functions that you have mentioned. But here at the first step, and for the sake of this talk, let's assume that this is the case.
Got it. Thanks.
Okay. So, believe it or not, it's a complicated problem. It takes me a lot of time to try to find these values, okay? And the way that we try to solve this problem is that, first of all, we introduce an alternative optimization problem called optimization 1. And in this problem, we try to find this. For each value of alpha, which is from 0 to 1, we try to find the maximum MMSE for each value of eta. Let's fix eta in the optimization 1. Eta is fixed, okay? For each value of eta and for each value of alpha, we try to find the maximum MMSE, okay, over all of the noise distribution that the probability of the acceptance is at least alpha. So is the definition of this problem clear? Okay. So this is optimization 1. And the first result is that we will show that by having access to the result of this optimization problem, we can calculate eta star, which is the best response of the data collector. Okay. This is a very surprising result. And the main reason is that if you note in the optimization 1, there is no notion of the utility functions. I don't care what is the utility function of the adversary and data collector. Okay. But even I mean, by having this, that this optimization problem is not dependent to the utility function of this player, if you know the answer to this optimization problem, you can use this and find the equilibrium of the game. So that's kind of surprising. Okay. By having this theorem, this result, the next natural step would be, okay, let's characterize this problem. Let's find the solution to optimization 1. Okay. So here is the optimization 1. C of eta of alpha, which is the maximum MMSE over all of the noise distribution that the probability of the acceptance is at least alpha. Okay. But you know what? Again, this problem is also challenging. And the reason is that the MMSE is a complex function over the noise. For any noise, you may have a very complex estimation function, which is the MMSE estimator. Okay, so MMSE is a very complex function of the noise. Okay. And in order to resolve this challenge, we again introduced another optimization problem called optimization 2. And optimization, and in this optimization problem, optimization 2, the estimation function is fixed. It is always y1 plus y2 divided 2. It's the mean of the inputs. Okay. Everything is similar to the optimization 1. Again, for each value of eta and each value of alpha, we try to find the maximum value of the mean square error for the case that the estimation function at the data collector is mean of the inputs, and the probability of the acceptance is at least alpha. Okay, so that's optimization 2. And the only difference is that the estimation function is fixed. Now the estimation function is not a complex function of the the noise distribution that the adversaries utilize. It's a much simpler problem. It's simpler problem comparing to optimization 1. And in lemma 1, we show that the result of optimization 2 is closely related to the result of optimization 1. And there is a vanishing gap between these two values. And this is vanishing gap because if you remember, and as you can see here, the M, which is the range of the computation, we assume that the range of the computation is by far bigger than the range of the accepted noise that can be injected by the honest nodes. Okay? So here, the left side, as M goes to infinity, it would be B of eta of alpha, and also the right side is B of eta of alpha. It means that, approximately the result of optimization 1 and the result of optimization 2 are equal to each other. Okay. And then in lemma 2, we find the result of optimization 2. And we show that the optimization 2, for each value of eta and for each value of alpha, beta would be h star of alpha divided by 4 alpha. And the h star is a upper concave envelope of this complex function, as you can see here. And all I want to note here is that, first of all, this function can be easily calculated. It is a little weird, but it can be easily calculated. And all matters in this function is the noise distribution of the honest node. So if you know the noise distribution of the honest node, you need to just do some calculation, basic calculation. Okay? And therefore, by combining lemma 1 and lemma 2, it means that we can fully characterize optimization 1. And that's all we want. Because if you remember, I've told you that if we know the result of optimization 1, we can find the eta star. And then through introducing another optimization problem, which was optimization 2, we could characterize, the result of optimization 1, which you can see here in theorem 2. Okay. So that's the high level, high overview of the proof. Is that clear? Okay.
I have a question, Hanzaleh.
Okay.
So I'm struggling with something, and then that's like it feels like it's wrong that we can increase M arbitrarily. For instance, suppose we have any computation, I could just ask the nodes to, instead of returning the computation, return whatever is the result times 1,000 or something, and that way get a better result in lemma 1. So and what I'm trying to say is how strong is this assumption that first of all mu is from this range, and what is the consequence of looking at these things from this lens? For instance, is there going to be some probability of failure at all times because lemma 1 can fail if mu is small, or we don't care about that? Can you talk a little bit about this range?
Yes.
So
yeah. Okay, so first of all, as I've told you, this is the first time that we try to utilize coding theory in the case that we are not in the honest majority. And in order to solve the first problem, we have some assumption here, and I'm pretty sure that some of these assumptions may not be the case for a lot of practical cases. I truly accept that. Okay. But here in this example, and by the way, for some of these assumptions in the next works, we have resolved them to, for example, we try to use some kind of machine learning based algorithms for the case that eta is not or the range of delta and M. Delta is not by far smaller than M, or eta is not in this range. We have some results for that too. But here we're assuming that eta is smaller than M. And if it's not the case, the lemma 1 is not right. And the whole theorem that I'm trying to say, the whole algorithm, the result, the first result, which I claim that by having the theorem 2 is not working. So that's the case. Theorem 2 is always true, but if eta or delta they are not by far smaller than the range of the computation, we can't use H star of alpha divided by 4 alpha as a good approximation of C of alpha. But still, result 1 is true. If you know the answer to of optimization 1, you can calculate the best response of the adversary and the best response of the data collector. That theorem is always true. Okay? Is that clear, Mo?
Yeah.
So
I
basically,
think like
yeah. Okay.
I'm
So
wondering
basically,
like
okay,
sorry,
go ahead.
go ahead. Yeah, I just wanted to say how important is like because like we don't see the detail of the proof. I was wondering like how important is like this assumption of uniformity. Like if the distribution is a little bit skewed to one direction, like how would it show up in this like bounds?
Okay, maybe I'm going to into the, I mean, not a very detailed, but a high level of the proof outline. Maybe after that, it would be more clear to you that what is the consequence of that. But I want to note here that the result 1 is always true. If you know the output of the optimization 1, that's all you want in order to find the best answer of the data collector and the best answer of the adversary. And also, in order to find the result of optimization 2, we try to sandwich, try to find a sandwich inequality to characterize this value by introducing optimization 2. And you're right. If, delta and eta are not by far smaller than the range of the computation, we may need to find another solutions. And this is the motivation of our next works. And for those examples, we try to find another ways. That's true. That's a very good question. Okay. Let's talk about the proof outline. So in lemma 1, we tried to find the relationship between optimization 2 and optimization 1, and we claim that we have this relationship between them. Okay. Again, it's a surprising result because in optimization 1, the estimation function is dependent to the noise distribution, while in optimization 2, it is a fixed estimation function. Okay. So it's a little weird. How can we relate these two problems together? The whole intuition behind this idea is that, okay, so the range of the computation for y1 and y2 is going to be between these, square, okay? From minus m, and also for y2 from minus m and f, okay? We show that for this green area, okay, as long as the noise of the adversary is symmetric for this green area, not for the whole area, okay? For this green area, the best estimation function is mean, y1 plus y2 divided by 2. We will show this. And here you can observe that if m is by far bigger than eta and delta, it means that this green area is almost all of the areas. Is that clear, Mo? Okay. So as long as G is symmetric, we will have this result. And that's a very surprising result because you know what? Because the noise distribution of the adversary and the data collector, the honest nodes, are not jointly Gaussian. So, but given this fact, but again, the MMS estimation function for this range is a linear function of the inputs. And we know, I mean, I'm sure that all of us know that the only case that the estimation function is a linear is for the case that the noise distribution are jointly Gaussian. But here we don't have such assumption, okay? But again, we have proved that for this range, surprisingly, perhaps surprisingly, the estimation function is y1 plus y2 divided by 2, okay? So that's the case. And this is an observation that connects OPT1 and OPT2. Because in OPT1, we have the best estimation. And here we are proving that, for a lot of cases, as long as, the noise distribution of the adversary is symmetric, the best estimation function is y1 plus y2 divided by 2, okay? This is an observation that connects these two optimization problems. And then we prove that by making the noise of the adversary symmetric, the adversary would not lose optimality, okay? So if the adversary is using some kind of non-symmetric noise, we can find a symmetric version of that non-symmetric noise that has the same utility. So it means that by assuming the symmetricity of the noise of the adversary, the adversary would not lose the optimality. And then by having the first observation, I mean, this green area, we will show that for any symmetric noise of the adversary, the difference between the MMSE, which is the error for the case that the data collector is utilizing the best estimation function, and MSE for the case that the data collector is utilizing mean as the estimation function, their difference is not that much. And it makes sense because, in most of the case, which is the green area, the error is the same, and the only difference is, those white areas. Okay, so that's the proof outline of lemma 1. Okay, and in lemma 2, we try to find the solution for optimization 2, in which we try for each value of eta and for each value of alpha, we try to find the maximum error that is injected by the adversary for the case that the data collector is utilizing mean as the estimation function, and we're trying to maximize this problem over all of the noise distribution that the probability of the acceptance is at least alpha. Okay. In order to find the solution of this problem, first, for this class of the noise, which you can see here, the adversary is utilizing kind of discrete noise distribution with the probability of the half. The noise value is Z1, and the probability of the half, the noise value is minus Z1. For this class of the noise, first, in order to have the probability of the acceptance equal to alpha, we show that in order to have this, we find the corresponding value of Z1, which is the position of the noise. Okay, and as you can see again here, it is all related to the noise distribution of the honest node. Okay, and we then show that for this class of noise, the MSE, okay, for the case that the data collector is utilizing mean as the estimation function, is h of alpha divided by 4 alpha. And the other two equations are related to the definition of h of alpha, which is, you can see it here. And again, all matters here is the noise distribution, the PDF, the probability density function of the honest node, which is public. Everybody knows that. For example, it may be, uniform, it may be triangular or whatever. Okay. Now let's assume that this is the curve of h of alpha. In the next step, we show that we can achieve the upper concave envelope of h of alpha by having this class of noises, which in the blue one, which are symmetric, but instead of, outputting just Z1, minus Z1, and Z1, we have minus Z2, minus Z1, Z1, and Z2 with some probability, okay? And we will show that by having this class of noise, we can achieve h star of alpha divided by 4 alpha, okay? And the probability of the acceptance is also for this class of the noise is alpha, okay? So it means that we have an achievability scheme here. It means that we could find a noise here that the probability of the acceptance is alpha, and the MSE is h star of alpha divided for alpha. So clearly it means that the result of optimization 2, we try to maximize the MMSE would be at least this number. Okay. And then we show that we can't do better. We will prove the converse. We show that we can't do better. And by combining two results, it means that the result of optimization 2 is h star of alpha divided by 4 alpha. So that's it. Okay. Now I'm going to talk about how can we calculate eta star. I'm going to talk about the result 1, which, by having access to the result of optimization 1, which is C of eta of alpha, how can we find the best response of the data collector and the best response of the adversary? Okay. Here is the plot for some example. We assume that delta here for all of these plots, colorful plots, delta is equal to 1. And also we assume that eta is from 2 to 8. Okay. And we assume that the noise of the honest node is uniformly distributed from minus delta and delta. Okay, so for the honest node, the noise is uniformly distributed. Okay, for this specific case, I mean, the scheme that the algorithm that we have proposed in the paper is for general noise distribution, but here for this example, let's assume that this is the case. Okay, and let's back to the example one. So these are the utility function of the adversary and the utility function of the data collector. Okay, just simple example. So this is the algorithm. In order, by having access to the curve of C of eta of alpha for each value of eta and for each value of alpha, by using these two steps, we can find the best response of the data collector. And this is the case. In a step one, for each value of eta for each curve, we try to find a point that maximizes the utility of the adversary. Okay, each of these green curves, green points, are the points that if, for example, the first one, if the data collector commits to the value of eta equal to 2, in a response to this choosing, which is eta equal to 2, the adversary would choose a best noise to maximize its utility. And in that case, the probability of the acceptance and the probability and the MSE would be a point which you can see by these green points here. And we will do this for all of the choice of eta. Okay. Then among these green points, we will choose the value of eta that maximize the utility function of the data collector. Okay. And here for this example, you can see that for this specific case, the best choice for the data collector is choose 6.75 as value of eta. And for another example, we can do the same. Step one, again, we try to find all of the points that maximize, the utility function of the adversary, and then we find the points that maximize among those red points that maximize the utility function of the data collector. And I want to note here again that for this example one, example two, what is fixed is all of those colorful curves. And those colorful curves are the result of optimization one. And that's why I told you that if I know the optimization one, optimization one problem's output, which is C of alpha, I can utilize this as a base point and try to find the equilibrium for any other utility functions. Okay. And for this example, we can calculate that the best choice for the data collector is to choose eta equal to 3.75. Okay. And by having the result 2, we can also find the optimal noise for the adversary. And as a result, you can calculate the probability of the acceptance and the MSE. And in example 1, you can see that the probability of acceptance is almost 80%, and the MMSE is 10, while in the second case, the probability of the acceptance is 20%, and the MMSE is 6. You can see the probability of the acceptance in the first example is bigger than the probability of the acceptance in the second example, but the MMSE is also bigger. Okay, I want to do some comparison here. Even for this simplest example, in classical coding, if you have two nodes and one of them is adversary, you can't output anything. So the probability of the liveness is always 0. You can't do anything. In analog coding, once you have two nodes and one of them is adversary, you can't output anything, because you cannot distinguish which one is detect which one is the adversary. All you can say that, one of them is adversary and I don't know which one is the honest one, so I can't output anything. Okay. But here, by utilizing game of coding, okay, we can, for 80% of the time, we can output something. And maybe that's a good thing. I mean, for some cases, okay, that's okay. 20% of the times, we don't output anything, so we have safety, but 80% of the time, we have both the safety and both the liveness. And here, these two nodes, they don't provide any proof. And they don't generate any proof for computation. So they don't need a lot of resources. They just need to do the computation. Okay. So that's it. I want to go to the next result, and I'm going to be fast. Okay, so do you have any question here?
I don't see any questions in the chat, but I think we are a little bit past time. So
Okay, so
we
I'm going to
have
be very fast here.
yeah.
Okay. Here I'm just want to prove that. So this scheme is kind of Sybil resistant. I mean, even for the case that we are in a trust minimized setting in which that you have multiple adversarial nodes, let's assume that you have n nodes and you just have one honest node, n minus one nodes are adversaries and just one of them is honest. So we have another result that is going to be published in the next week that even for this case, I'm not going to talk about the details because of the time. We will prove that in this case, there is no gain for the adversary by having access to lots of adversarial nodes, and there is no pain for the data collector. So for the adversary, having access to n nodes is similar to having access to just one node. And for the data collector, that's a base case. I mean, the system is kind of Sybil resistance. Okay. And this result will show the power of the game of coding framework in the decentralized application cases in which trust is a very scarce resource, and people do all sorts of crazy things, and you need to be careful about this kind of Sybil resistance. The adversary may have access to a lot of resources. But here we will show that we can define a system that even for these cases we have a very good result. Okay, and this is the proof outline. Okay, I'm not going to talk about it. If you're interested, if you're interested, we can talk, after the meeting. Okay, that's it. And for the next step, we will try to find a solution for the case that the region of the acceptance is more general, and we show that for the case that the region of the acceptance is not just y1 minus y2 smaller than eta delta, it's any function of y1 and y2, we show that this is equivalent to a mixed strategy instead of pure strategy by the data collector. And also for the case that the game is not complex. So here we assume that the data collector knows the utility function of the adversary. For the case that the data collector even doesn't know what is the utility function of the adversary, we are using multi-arm bandit solution to find the best response for that. And surprisingly, even for those cases, we can choose the best strategy to commit in the blockchain. And then here in this problem, we have utilized repetition coding, and we have some result for the case that instead of using repetition coding, what if we have we are utilizing more advanced and complex coding techniques, and we have some results for that. So that's it. Thank you very much for your time. And okay.
Thanks a lot, Hanzaleh. I think like what this work is trying to achieve is something truly magical, in the sense that as you had on one of your last slides, even if you have one honest node in this simple repetition coding, and the system your framework tries to maintain safety and maybe achieve lightness sometimes.
Exactly.
And to achieve this magical thing, we need to make some assumptions, and
yes.
It's fair. Yeah.
So there are a lot of steps and a lot of problems that need to be solved. But what I'm trying to say here in this work, in this first work actually, is that if you want to have, for example, ZKML, decentralized machine learning, so all they do is to outsource the computation, and they force the external nodes to generate a proof that they have done everything in the right way. And it's not a good behavior, because the proof generation task is very complex. It's very resource intensive, and maybe this scheme leads to some kind of centralization, because there are not a lot of nodes in the world that can have access to these resources. Okay, instead of, for example, outsourcing the computation to a node that can do 40 times bigger, than the computation itself, let's outsource the computation among 4 nodes, 10 nodes, or whatever. And they don't need to generate the proof. They just need to do the computation and send you back the result. And as long as you have a good mechanism here, you have designed a good mechanism here, rewarding the good behavior and slashing the bad behavior, at the equilibrium of the game, okay, the consequence would be that most of the time, of course, based on the utility functions of the players, the system is live. And whenever the system is not live, you're not, compromising safety. The system is always safe, but most of the time the system is live. So that's the main intuition behind this work. And if you want to use classical coding, there is a fundamental limit in classical coding. All of the results of the classical coding is for the case that you have honest majority. And here we're talking about, the trust minimized cases, or for the case that, we're not necessarily in a honest majority regime. So that's the intuition behind this work. And the advantage of this work comparing to the OML is that the latency, in the OML, so you need to wait for the fraud-proof challenge period to make sure that everything is good. And of course, that will work for a lot of cases. But for the case that the latency is important, so I think that utilizing game theoretic viewpoint and these kind of solutions works better. So that's the main message of this work.
Great. Any more questions for Hanzaleh from the audience? Unfortunately, we lost some of the audience. If not, we can wrap up. Thanks a lot, Hanzaleh, for the presentation. Personally, I really like this work, and I think it may get some time before you and maybe the broader research community find the best fit for this approach. But I'm sure it's going to be very helpful in certain scenarios. And it's definitely a new way of thinking about the problem. Thanks a lot, everyone. Hope to see you next week.
Thank you for having me. Thank you, everyone. Bye.